Hello everyone, thank you for joining our GeoScience and GeoEnergy webinar of the 20th of August 2020. I'm Maren Brehme from TU Delft, a colleague of Hadi who couldn't make it today. He's on a Weld certification. It's my pleasure to host you all together with Sebastian Geiger from Heriot-Watt. We are especially grateful to all our keynote lecturers who accepted our invitation and to all of you for joining us this week and combat work from home isolation. Please subscribe also to our YouTube channel, which allows you to see all the upcoming talks. To our student attendees, please attend the Porous Media Tea Time Talks series to share your research and broaden your network. Now to the lecture. We are pleased to announce our keynote speaker of this week, Professor Christopher Jackson. Christopher is an Eckner Professor for Basin Analysis at Imperial College. He completed his bachelor in 1998 at the University of Manchester, where he also did his PhD, then finishing in 2002. After that, Chris was employed as an exploration research geologist at the Norsk Hydro Research Center, now Equinor, in Bergen in Norway. In 2004, he moved to Imperial College and since then has focused on using traditional fieldwork techniques and seismic reflection data to study the tectonostratigraphic analysis of sedimentary basins. When not being busy with studying rocks and the ways in which they deform, Chris gives geoscience lectures to the general public and in schools. He appeared on several earth science-focused television productions and podcasts. On top of that, Chris is actively engaged in efforts to improve equality, diversity, and inclusivity in earth science in particular, and also in higher education in general. He's very active on Twitter right now, so have a look on that also. It's our pleasure and honor to host Chris in our GeoScience and GeoEnergy webinar of this week. To the audience, please note his lecture will last for about 30 minutes, followed by questions and a discussion. Like before, please type your questions in the chat room, and Sebastian will go through them after the talk. Chris, thanks once, and the stage is yours.
Okay, thank you very much. Hopefully everybody can see me and can see my slides as well. Yeah, so it's a great honour to give a talk. Science continues in the face of COVID, and we're all adjusting to that, but it still gives us a chance to chat about things we care about and get feedback from the community. So technology is our friend in that respect. Yeah, so today I'm going to talk about salt tectonics, and for a change, I'm not going to talk about where salt is. So these big salt structures you may have heard of. Salt diapirs. I'm going to talk about where salt isn't. So I'm going to talk about a process known as salt welding, and this is when salt disappears. This work is work I've done collaboratively with the people mentioned on this first slide. So Clara Rodriguez was a PhD student at the university where I work at Imperial College, and Yu Zhang was a master's student at Imperial, and then a range of other people I've worked with named there. And I'd just like to say thank you to PGS, CGG, and AMP for providing data and Schlumberger for patrol software. So I'm going to try and make this talk as inclusive and as accessible as possible by kind of going through some of the key terms and definitions to bring everybody up to speed with this rather bewildering nomenclature we have for salt tectonics before then applying some of that to a couple of different case studies. So what is a weld? So a weld is the structure joining two rock bodies that were formerly separated by salt. And that's a term from Martin Jackson and Collis Kramers from 1989. So what does that actually mean? So let's take an example here. So here we can see a pre-salt layer in gray, a pink salt layer, and that salt can flow. And we've got these blue mini basins labeled here, which is subsiding down into that salt. Through time, those mini basins, because they're denser than the salt, they subside into the salt, and the salt flows in to feed these features here, which are called diapirs. And eventually, those mini basins in blue sink all the way through the pink salt layer to come into contact with the grey layer underneath the pre-salt. And that red line there is this thing called a salt weld. So you can see it's a structure joining two bodies of rock that used to be separated earlier in time by a layer of salt. So we have a number of different types of welds. So we look to what we call here a primary weld. So a primary weld forms at this level here. So this is where this mini basin I'm indicating here has subsided through this pink salt layer between these two diapirs and has come into contact with the pre-salt layer in dark brown. We have a secondary mini basin, and this is where we have a sub-vertical weld. So you can see that this weld, this red line, used to be between a mini basin on the left and a mini basin on the right that are now in contact because we've squashed the salt out of the area where the red line is. And on the right-hand side, you can see a seismic reflection example where we can see a mini basin on the left, one on the right. There's this subvertical weld in here, which is a secondary weld with salt above it and salt below it. And finally, we have this thing called a tertiary weld. Now, this forms at the shallowest part of the salt tectonic system. So it forms where a mini basin has subsided through what we call allochthonous salt. So this is salt which has flowed out in the form of like a salt glacier. And we can see here that this mini basin has subsided through to come into contact with this older mini basin here, and that's what we call a tertiary weld. And you can see the attitude, so the dip of the tertiary weld is very similar to that of the primary weld. It's subhorizontal, but it's at a shallower level in the basin. It's shallower up there. So what do these look like in the field? So I'm going to show you an example of a secondary weld, and this slide is going to highlight the issue of scale when we're trying to understand salt welds. So we can see here in green, we're going to look at a secondary weld, and this one here is from Lipopa. And here we've got a mini basin on the right with rocks dipping to the right, a mini basin on the left with the rocks dipping off to the left. And then the red line between the two is an area where there used to be salt. There used to be a diapir between these two mini basins before those two mini basins are squashed together and the salt was squashed out. What you can't see from here, from this aerial photograph, is the salt that's left in there or any of the material there. And that's because we're at a very big scale. So imagine in your minds you're using a seismic reflection data set. So this is a geophysical tool looking at something which is very detailed from a very long way away. But if we kind of go down onto the ground, and I'm going to take an example here from the paradox basin, so it's not from the paper, but it makes the same point. When you actually zoom in, and you can see a person of the scale here, here's that secondary weld. There may be just a little lump of, in this case, anhydrite or gypsum, in this case, between a mini basin on the right and a mini basin on the left. So this is what could be left. You can see it's only a few meters thick, which is why with the seismic reflection tool we typically use in the subsurface to look for these, we'd have problems because these things are essentially subseismic. So let's think a bit more about some other weld terminology. So we've looked at primary, secondary, and tertiary. So there's different degrees of completeness of welding. So a complete weld is shown here. This is where there's absolutely no salt left in the weld, in this primary weld case. We then can have an incomplete weld. So look at the cross section on the right. You can see there's a little pink sliver beneath the mini basin and above the subsalt rocks. And that's what we call an incomplete weld. And that's where we have 50 meters or so of remnant salt left in the weld. And then we can have a thing called a discontinuous weld. And this is where we have patches of complete welding, shown by the black dots, and little pink bits of salt left. So you can see there's a patchy weld there, and in the map view, it shows you the difference. You can see there's areas of deep pink with light pink. So there are three terms I sort of would like you to carry with you through this talk: complete, incomplete, and discontinuous. And apparent is the final term, and apparent means that at the scale of observation, the weld looks like there's no salt in it. So like imagine that aerial photograph I showed you from the previous slide from Mexico. If you're in that area, if you're in that helicopter, it might look to you like there's no salt left in there. But it's going to be important as we go through this talk to realize that we don't get to see everything we need to see sometimes with the tools we are using. So when we think about this process of salt welding, what's actually happening in terms of the kinematics and the mechanics within the salt layer itself? Because obviously the salt is flowing out. So we can take the earlier stage, we might have solid state flow. So we'll have crystalline creep of the salt layer in here. And these purple layers here are maybe stronger carbonates or anhydrites that are floating depositionally within the halite, the red color. And as we thin that salt even more into stage B here, we can see we start to boudinage and break up the anhydrites and carbonates, and the mini basin's coming down and almost welding with the pre-salt until it does. And at which stage we might actually have dissolution taking over. So we go from solid state flow of the salt into a dissolution-driven removal of the remnant salt, and that could remove all of it. So why do we care about this? Well, evaporites are a really important seal for both hydrocarbon resources, but also in CO2 storage sites. As you can see here, they have phenomenally low permeabilities, lower than chalk and lower than clay stones. So these are really important cap rock. And they work like this, they impose boundary flow. So we can have permeable material underneath, and you can see here this salt layer is stopping these fluids or these gases going into the overburden. But we can damage the salt and fracture it, and also have grain boundary porosity forming, which we can have very low rates of flow of gas or fluids through the salt itself. So it's important to know how much salt is left, but also what it's made of. So just one other slide before we kind of get into this. Why does this matter again? Well, imagine if this weld here is sealing in red, and we have source rocks below the salt, and we have our prospects above the salt. If that weld is sealing, so it's thick and halite rich, we'll get an accumulation below the salt, and our prospects up here will be dry. If this primary weld is leaking, but our secondary weld is sealing, we can migrate through the weld from our subsalt source rocks up to our reservoir here, but we'll have a dry prospect further up dip. And if both of these welds, the primary and secondary weld, are open, so we can flow hydrocarbons or gases, hydrocarbons through them, we then can fill this accumulation at the shallow depths. So it's really critical to know the composition and thickness of material left in welds. So how much is left, what's the composition, and what might we infer about the processes occurring during welding? Well, let's take a case here before we dive into the case studies of a suprasalt layer here and a subsalt layer here, and this is a pink halite. And as we're squeezing that salt, we deform it via this kind of flow profile in through here, this Poiseuille flow profile. If we add these medium viscosity layers, so let's put a bit of anhydrite in that salt depositionally, could have been deposited with the halite, we can see this much more tortuous flow profile. And if we then put in some high viscosity layers like carbonates, it really kind of slows down and makes the rheology of the salt overall more sticky, more viscous, and harder to expel. But critically, if we start to squeeze that salt, what you can see is we expel the low viscosity halites and carnelites and sylvites, so potash salts. We can push those out, and we can volumetrically enrich the weld in these more higher viscosity and brittle layers. And that's important because those brittle layers can be damaged in a different way and could allow flow through the weld. So we need to know what's in the weld as much as we need to know how thick it is. And we're going to probe that now with two case studies from using seismic and borehole data from Southeast Brazil and the Gulf of Mexico. So let's go to Brazil. This is offshore Santos Basin, offshore Brazil here. So this is Santos Basin. This is a large 3D seismic reflection volume. And I'm showing you an image here of the top of the salt. So the red areas are where there's these large diapirs, these big buildups of salt. And the areas between them are these mini basins, like I showed you earlier on. So this is where sediments have sunken into the salt. This is a huge area. This is 20 kilometers for scale in here. And I'm going to use two boreholes in this part of the talk as well. One borehole up here in the northwest and one in the southeast. So let's have a look at a seismic profile which goes between borehole A and borehole B. Now I'm going to animate this, and you'll see here's the salt in pink, here's the pre-salt layer in green, and these are the mini basins that have subsided into the salt to create these large pink bodies here, these diapirs. Now I'm going to animate from left to right, and you'll see borehole A goes down into a deep mini basin through where the salt is welded, and borehole B, that will come on the right hand side, goes through an area where the salt is relatively thick. So it goes very quickly, this. But there's borehole A going down through the salt, and there's borehole B through an area where the salt is thick, the pink layer is thick. So let's go and have a look at the mini basin in A where that well was drilled. So I'm showing you two maps here. On the left-hand side is a top salt structure map. So that's the same map as I showed you before at the regional scale. And it's 5 kilometers for scale. Red is towards you, is shallow, and purple is deep. And we can see here's the mini basin here outlined with the white dashed lines. There's borehole A drilled right in the heart of the mini basin, which is surrounded by these big salt walls. So it's a big, deep mini basin, 5 kilometers deep or so. If we look at the salt isochron, so this is showing you the thickness of salt, we can see there's the thick red areas, that's where the diapirs are, and the white areas are where the salt is missing. So that's where the salt is apparently welded, the white areas. And lucky for us, you can see the borehole A goes right through one of those white areas. But we can also see, if we look at this salt thickness map, that this is what we call a discontinuous weld. So this is one of those terms I asked you to carry with you in the talk. It's not an area where it's completely welded. It's not an area where it's incompletely welded. It's an area where there's patches of both. So these are apparent patches and it's overall discontinuous. So now I'm going to show you a seismic profile which goes from the northwest to southeast through Borehole A. So here's that location map for just to keep you orientated, and the section I'm showing you is there. Here's Borehole A going down through this thick mini basin. You can see it goes down through the bottom of the mini basin, through the salt. Top salt is in pink, base of salt is in green and goes into the subsalt. And at the scale of observation of this seismic reflection profile, this is 2 kilometers per scale, 200 milliseconds for depth, so about 300 meters in the true vertical. It looks like it's apparently welded, like there's no salt left at the bottom of here. There's thick salt here on the left, thick salt in the diaper on the right, but no salt where the Borehole A was drilled. Now I'm going to show you a seismic profile going through here. So it's going to be a northeast trending profile crossing Borehole A. So here is that profile. Again, there's your location map for orientation. There's the big deep mini basin again, bounded by this salt stock, the salt diaper on the right. And here we can get a real sense of how discontinuous that weld is. Borehole A just happened to go through an area where there's seemingly no salt, but we can see these little bits here and here and here, these little pockets of, in this case, Actian, so early Cretaceous salt, sitting in the base of the mini basin. So it's this discontinuous weld idea. So let's go and have a look at what's in that well, because we have petrophysical data from there, we have some cuttings data, so now we can go and interrogate both the thickness and composition of material left. So here's a zoom in, so I've gone right down into details here. Here's top salt still in pink, base of salt in green, and you can see that those two seismic reflections that we've mapped come right next to each other, which is the white area on the thickness map. So it looks like there's nothing in there. So let's go and have a look at the borehole data. What we want to focus on here is this unit here called the Oriri Formation. This is the early Cretaceous salt. Scale is important here. This is 10 meters. So the Oriri Formation here is just over 20 meters thick. We've got caliper, gamma, neutron density, and neutron density and sonic data here. And we can see the lithology calculations we've done from the cuttings and the petrophysical analysis show there is no halite in the weld. It is dominated by anhydrite, carbonates, some sandstones, and a little bit of marl. So proportions-wise, it's 40% carbonate, 40% anhydrite, and a bit of clastic material in here. So in summary, it's 22 meters thick, there's no halite, and these are the most significant lithologies. So think back to the kind of outline at the beginning of the talk, thinking about what's left in the weld. I made this argument that because of the mechanical properties, the rheologies of the material in salt, there'll be differential evacuation, and that data is starting to point to that here, in that all the halite is gone, and all that's left is non-halite lithologies. So now let's compare Borehole A to Borehole B. And Borehole B, remember, was drilled in an area where the salt was very thick. It's important to remember that Borehole B is not drilled in the salt structure immediately next door to this mini basin, the Parachi mini basin. It's drilled down dip, but we believe Borehole B, the lithologies in there, is representative of areas of thick salt. So what I've done here is I've rescaled this. So this is Borehole A, which I showed on the previous slide, and I've rescaled it here so it looks super silly and super tiny. Why is that? It's because the scale bar here is 500 meters now. Remember, the salt in Borehole A was only 22 meters. So let's show you Borehole A, and you can see it's huge, right? There's almost 2 kilometers of salt in that area where the salt is inflated. As important as the thickness is the composition in that area. You can see that all of these layers in the salt, and don't worry about the terms in here, A1 to A4, you can see that there's between 97 and 70% of the salt here is dominated by halite. Not only that, there's also hardly any anhydrite. There's a little bit of anhydrite, not much, up to 10% in the upper part of the salt, but also no carbonates or plastics. So this is a halite-dominated part of the salt body. And that strongly contrasts here with what you can see on the left, in the top left here. So compositionally very different, and thickness-wise very different. So why is that? So let's think about a genetic model for weld formation. So what's happened as the salt is welded? So we have a pre-thinning salt scenario here in stage 1. We've done lots of different work on the salt offshore Brazil, but I don't need to go into that here. All I want you to take from this is there's a number of different intrasalt units, and some of them, like A2, have more carbonates and hydrides than other units like A1 and A4. So we're going to start to thin the salt in stage 2, so that mini basin is pushing down on the salt. And what you can see straight away is happening, we're starting to push out and thin preferentially the halite layers, but the blue carbonates and hydrides are retaining their thickness because it's not as easy to expel those as it is the less viscous halites. We eventually come to a time of salt welding, so this would be our 22 meters, and all we're left with in the weld is carbonates, anhydrides, and plastics, and all the other material has been evacuated out. So this process of welding has driven a complete change in the Heriot formation's lithological and mechanical character. What's happened elsewhere? Well, the blue arrow is showing you that all that halite, what it does is it flows into those diapirs and pumps them up, makes them really big, really thick, and creates these really obvious bodies. And this term, which was coined in 1968 by Kupfer, differential purification by movement, is a bit of a mouthful, but it seems appropriate here that we've had differential purification of the original parent salt layer by the kinematics flow of material within the salt. This model is idealized, obviously. It's likely that some thinner materials, anhydrides and carbonates in the salt may have been carried up buoyantly, even though they're denser. They could have been carried up buoyantly into the surrounding salt bodies. And also, we're showing here that these layers here are thicker than in here. And that's probably not the case. These could be just as thick or thinner slightly than the parent salt layer. But it does represent what we think are the main processes going on during salt welding. So let's just conclude on that first case study before we move to the second one to conclude the talk. So how much salt remains in an incomplete or apparent weld? Well, the weld data proves that there's remnant subseismic salt in an apparent weld. And we would argue that the term apparent weld should be used until you actually have borehole data to unequivocally prove the absence of salt. Seismic reflection data, no matter how awesome it is, may not tell you the whole truth. What is the composition of salt in this incomplete or apparent weld? Well, it's halite poor and it's rich in these evaporite-associated lithologies. And so the learning from that is it's really important to know what's in your autochthonous layer to then try and predict what the weld thickness and potential sealing properties are. Because obviously, if you only have a halite, 100% halite autochthonous layer, you may only have a little bit. You'd only have halite left in your weld. You can't magic and anhydrides and carbonates out of thin air and put them in the weld. Equally, if you have a very heterogeneous autochthonous salt layer to begin with, you may expect your weld then to be similarly heterogeneous, both in terms of their lithology, mechanical properties, but also maybe their sealing potential. And what might we infer about processes occurring during salt welding? It supports these analytical and numerical models, which kind of suggest that a few tens of meters of salt will be left in the weld due to the fact that there's drag imposed to the boundary layer. So where the salt is in contact with the overlying stiffer rocks and the underlying stiffer rocks, you get drag at those locations. And this idea of differential purification by movement seems appropriate here. So let's now move on to our second case study. So now we've got this thought experiment, haven't we, where we've looked at this primary weld in the Parachi example, and we've kind of looked at some field examples of a secondary weld, and now we're going to go up to the tertiary weld level. So the hypothesis you can build here is that, okay, if we're squeezing out all the halite from the autochthonous layer, by the time that's flowed up the diapirs and into these allochthonous layers up in here, it should be super halite rich, shouldn't it? Because we could have left all that junk or the non-halite material behind. So we've at least got a kind of thought experiment that we can sort of go and test with another data set. And that data set is from the offshore Gulf of Mexico. So this is where we're going to be. This is a regional seismic profile, and I've shown the approximate location and study area here. Here's the seismic profile. I know there's going to be like engineers and non-structural geologists and people. Don't get freaked out by this cross-section. All I want you to take from this is it's a super complicated salt tectonically influenced part of the world. For the specialists out there, there are two layers of salt in here. There's the Luan salt, which is Jurassic down here, and then there's this shallow salt in here, which is part of something called the Sigsbee canopy. What we're going to be looking at is a position sort of here, okay? So we're going to look at an area where this shallow mini basin subsided through the Olocthenous salt to create a tertiary weld. So remember, the tertiary weld is the shallowest weld forming in our salt tectonic system. So that's what we're going to go and look at now. So here's a seismic reflection profile through the study area, west to east. This is for scale. This is a depth migrated volume. So this is 2,000 meters there, 2 kilometers in this orientation. So let's see, autochthonous salt down in here with the primary weld. Feeders, so these are diapirs. We call them feeders because they feed salt up to the shallower level, to the Olocthenous salt level, the canopy. You can see there's lots of salt up here. We have a subsalt mini basin. So these are the first generation mini basins that subsided through the salt and welded down onto the pre-salt. And then we have these supersalt mini basins which subsided through the Olocthenous salt and are now in contact, as shown here, with the subsalt mini basins across a tertiary weld. So let's look at the base of salt. So I'm going to show you, this is a map of the blue horizon. And you can see purple is deep, red is shallow, and we can see the purple areas are probably where salt flowed up to feed the shallow salt level. As important, I think, is the top salt. So this is the top of the Olocthenous salt. We can see these red areas are where the salt is relatively, the salt is relatively shallow, and purple areas where the salt is relatively deep. And this is where this mini basin is. And what I want you to see in here is the well. So this is the AT8 well, and this is critical for the next bit of the talk. So you can see where it's drilled. It's drilled through an area where the salt is relatively deep. Not only is the salt relatively deep near the well, as shown here, now I've animated in a salt isopack, so this is the salt thickness. It's an area where the salt is very thin. So the purple is where the salt is thick, so this is where the big canopy is, and the red is beneath the mini basin where the salt is thin. And you can see the well is drilled almost in that white area where the salt is, according to the seismic data, completely absent. So let's take a seismic north trending profile going through the well to get a bit of the structural geology context of that well before then we dive into the details of the well. So here we are, again, lots of complex structural geology on here. Don't get too hung up on some of the stuff in here. The main point I want to use this slide for is to show you, here's the AT8 well, because it goes down through the supersalt mini basin and then down into the subsalt basin. It was targeting Miocene deep water reservoirs down in here. Top salt is in red, base of salt is in blue. You can see the pink salt body is shaded in pink, and you can see they come together so that there's a tertiary weld between this mini basin above and this mini basin below. So let's zoom in and look at some of the data in the well. Scale is important again here. This is 20 meters for scale, so this is about 100 meters of thickness. We've got caliper, gamma, density, P-wave and resistivity data through the well. We've got an upper Pliocene to Holocene clastic dominated interval in the upper part. We've got an upper Miocene to upper Pliocene to upper Miocene succession in here. So sorry, these tracks are starting from about 4 kilometers in the well. So I'm just zooming in around the tertiary weld. And then we have this area in here, which is far more enigmatic, I would say, in terms of the petrophysical characteristics. You can see all the tools are swinging back and forth and doing quite odd things compared to these more consistent readings we have above and below this interval of interest. So let's zoom in on the next slide to that interval. So all I'm showing here is gamma and density data. Again, scale is important here. So each of these increments is 5 meters here. So what can we see? Well, if we cross-plot all the data to the neutron density data, we can see some clusters falling out. We have a bunch of data here which are related to the clastic material above and below this rather odd interval in here. And that's that material in here. And then we have this other material in here which has relatively low density and relatively low neutron porosity values in here. And that's the halides. So these are very strong petrophysical indications of it being halite. And you can see there's an upper halite layer in here and a lower halite layer in here. This upper layer is about 5 or 6 meters, and this lower unit in here is about 15 meters. And in between them, there's this very odd mudstone layer in here, which has petrophysical characteristics similar to mudstones above and below. So that's the top salt there, and that's the base salt in there. And they're defining an apparent weld. And why is it an apparent weld? Well, if we go to the seismic data again, now I've zoomed the seismic data right into the weld, and let's just do some animations here. Here's top salt, here's base salt, there's that upper mini basin and the lower mini basin, there's the well. And you can see we're forced to bring our two seismic reflections together, so we think that there's a weld in here. And we can see that the weld is clearly below seismic resolution, and it's not defined at its top and bottom by discrete reflection. So that makes seismic mapping of welds challenging. We see a change in the polarity between black and white of the weld, and we think that's because not only is the weld probably changing thickness, but we're also getting changes in acoustic impedance driven by changes in the material above and below the weld. So depending on whether there's sand over mud, or mud over sand, or sand over salt over mud, you get different seismic responses depending on the salt thickness and presence, and also the composition of materials above and below. And then we have this rather odd layering here. So just before I finish, I'll show you one of the kind of strange bit of data. So again, this is kind of interesting in terms of the salt composition of the weld composition and thickness. The biostratigraphic data, I'm not going to spend too long on this because, but just in case there was anybody who's interested in salt tectonics and stratigraphy, this is age data. So this is age here, this is depth in here, this is increase in age downwards, which is good, because otherwise I'd lose my faith in geology if the rocks got younger going downwards, although they can, obviously. But we see a downward increase in age from Pleistocene rocks to Miocene rocks overall within the borehole, apart from these rather bizarre samples in here where we have these 3.5 million year old samples encased in samples which are 2 million years. And these are not due to caving, because caving normally introduces younger rocks down inside older rocks as you're drilling through the succession. But these are older rocks encased in younger rocks. And we've got some bugs in here which constrain the ages. That's right where the salt weld is. And we thought this was quite weird when we found it, because we didn't go looking for this, but it looks like there's these very odd old rocks sitting just above the salt weld. And if I show you the seismic profile, again zoomed in, you can see those green samples, the green samples here. And I've just indicated on here a blue sample shallower in the borehole, which is this one here. So all these old samples are here, and we think it's something to do with how the diapir is inflating. And the diapir, as it's growing, has old material in its roof. So it's kind of like gets smeared with older material that then kind of gets brought up as the diapir is inflating. But at the same time the diapir is inflating, the mini basins around it are subsiding. And then as you break up the material above the diapir, you put those older sediments into younger sediments. So we think that this is actually telling us something very important about the age of welding, but also the process by which welding occurred. So like I said, that's a bit of an aside, but I'm happy to take questions about the importance of those age data. So to conclude, so what is the composition of a tertiary weld? So we looked at primary weld to start with, and now I've shown you this tertiary weld. Well, in contrast to the Parachi primary weld, this is halite dominated, although it has this rather enigmatic allochthonous mudstone inclusion, which I'm happy to take questions on. Broadly speaking, what we found in the Gulf of Mexico example is consistent with the model predictions, which were that at shallower levels in the salt tectonic system, you may expect to find more halite-dominated welds. The problem here is there's very little primary weld data going down through the autochthonous salt. So we don't know if the autochthonous salt, the Luan, was only halite anyway. It's unlikely it was, but if it was, then it's probably no surprise that the tertiary weld here was halite dominated. So there's a caveat there. So, this is the model we drive with, as you go from primary to secondary to tertiary levels, you'll have a decrease in carbonates and anhydrites and an increase in the halite composition. Obviously, if you're drilling through salt, it's useful to have these to try and risk prospects at those different structural levels. How much salt remains in a tertiary weld? Lo and behold, 24 meters, several tens of meters is what the analytical model suggests, and that seems consistent again here. We had 22 in Parachi in Brazil, we have 24 here. And so, is this increasing amount of data we have, is this suggesting that all seismically defined welds we're looking at are actually all apparent or incomplete? So we always should be assuming there is some material left between our seismic reflections. And how is this tertiary weld expressed in seismic reflection data? Well, it's really bloody complicated. Because of the changing lithologies above and below the weld, and because the weld itself is changing in its lithology and acoustic characteristics and thickness, it can drive quite a lot of changes. And we've done some work with seismic forward modelling to look at all of the different ways welds can be expressed as a function of those different characteristics. So thank you very much. That's about just over 30 minutes. So I hope that talk was informative and useful, and I'm happy to take any questions you might have.
Thank you, Chris. Thank you very much for this great talk. I think it was quite inspiring, and I learned a lot at least. And I guess there will be several questions, so I hand over to Sebastian to chair the questions and answer session.
Yes, thank you very much, Chris. And as someone who started out as a geologist and then ended up as an engineer, it's really nice to see some really cool geology. So well explained. So thank you for that. Everyone, please do put your questions into the chat room for the Q&A session. The first question is from Kirsty Wright. Hi, Kirsty. And the similar question that I had is it possible to estimate when salt wells occurred or how long it took to form?
Yes, absolutely. So it is possible to work out when salt welding occurs, and the trick seems to be, based on the work we've done, is not to look at the salt, it's actually to look at the mini basin above it. Because the mini basin, which is subsiding into the salt, will contain a record of the way the salt is flowing out from beneath it. So what we've seen I'm going to make it very simple before I make it more complicated. The simplest case is when the mini basin is subsiding into thick salt, it will be defined by a series of bowl-shaped wedges of stratigraphy. So we'll have nice, perfect bowls because the salt is flowing evenly out from underneath it. When that salt welds and the mini basin touches down on the underlying material, we can have a process known as turtling. And what can happen there is the mini basin can essentially unfold because you take salt from the sides of the mini basin. And this will all be recorded in the stratigraphy of the mini basin. So you'll go from these bowl-shaped sequences to more wedge-shaped sequences like that, if you can see me. So if you can map that change in the seismic stratigraphic architecture in the mini basin, that can often tell you about welding. Now, what the problem is with that very simple interpretation is that mini basins don't subside on their own. Usually you find mini basins subsiding as part of an array, and they have kinematic interactions between them. So mini basins can start tilting before they weld. They can start tilting as they're subsiding due to other processes. So you have to do quite a lot of detailed work to make sure that the driver for what you're seeing is due to the welding process. What I would argue, though, is turtling, this process of turtling is fairly diagnostic of welding. So I would look for where a turtle formed, and that's again defined by changes in thickness. So hopefully that answered your question. The other cool thing as well, Kirsty, is how long it takes for salt to weld. There are some flow rates imposed by the viscosity of the salt. So there are some analytical solutions that would say, this is as fast as the salt can move based on its viscosity. And that obviously depends on how thick the salt is to begin with and how dense the mini basin is, right? So there's some moving parts on there. Some work we've done offshore Angola suggests that welds, which are very big, say 50 kilometers long by 20 kilometers long, take about 150 million years to form. Because the mini basin subsides really slowly. It can weld at one end and then it kind of slowly subsides at the other end and then eventually welds. So that can be an incredibly protracted process. And if you want to risk prospects, you need to know obviously when the weld formed. So you need to know when that happened.
Thank you, Chris. Many questions coming in, and Martin Blunt, also Imperial College, one of our former speakers, engineer like me, about geology today, so you're inspiring. So I take the opportunity to ask as a chair very quickly follow-up question from Kirsty. And when I did my PhD at ETH Zurich, there's a huge group who did modeling of salt diapurisms, mathematical modeling. Is that something that could help you to understand some of those timescales? That's still something that's being done, or has that disappeared, that field? No.
It's all being done. There's lots of there's geomechanical models, but there's also things like discrete element modeling being done as well. So all of those take sort of off-the-shelf, experimentally defined rheologies for salt and then code them in as a kind of condition. And so they do tell you about the rate at which salt can flow, and therefore for a given thickness of mini basin, for a given density, how long it would take for the weld to form. Yeah, so that's still being done, and there's a large group of people doing that.
Okay, thank you. So over to our audience, Kieran Blacker asks, are there constraints on the length and scale of these welds? The examples you've shown are enormous. Are they always that large?
No, they can be, yeah, so all the examples we've looked at here are just like seismically imaged, so seismic scale examples, so kilometers to tens of kilometers. But obviously, I mean, my feeling would be, Kieran, is if you go in the field, and I know this from some of the papers from La Popa, you can walk along bits of these salt welds and there'll be a patch of gypsum. And remember, it's gypsum because all the halite's been dissolved when we're in the field often, and the anhydrite has been rehydrated back to gypsum. So you get these blocks of gypsum, and you'll walk 10 meters along the weld, and suddenly there'll be no gypsum, right? So both rocks, the wall rocks, will be against each other. Then you'll walk a bit more, and then there'll be another patch of gypsum. Now, what does that mean? It probably means the weld is discontinuous, but it also could be slightly a function of variable preservation of materials as exposed at the Earth's surface. Now, what you obviously want is a very, very densely drilled example from the subsurface where somebody sampled the weld in numerous locations, because if we just say the seismic data is garbage, we can't work out anything using it. With the weld data, there's just not many examples that we've had access to where it's been densely enough sampled to see what the length scales of the welds would be.
Okay, thank you. A question from Anne. Thanks, Chris. Interesting talk. I concur with Maren. I learned a lot. Do you have an idea how one would estimate if a weld is sealing or not?
If somebody was paying me a lot of money to, I'd probably take a guess on it, right? I think that, I mean, the whole point of this research we're doing in this talk, and hopefully I communicated it clearly, is there's a series of observations you could make which would help you, within some numerical space, risk that prospect, right? So let's take two cases, right? So you're risking a subsalt prospect near the basin margin, near the salt basin margin, where you know the salt is very heterogeneous and contains lots of carbonates. And in the seismic data, you see an apparent weld. Now, my fear there would be that weld would have brittle materials in it, which could fracture, and therefore the risk for that prospect would be higher than a risk for a prospect maybe where we're looking at something at a tertiary weld level, where we think the weld might be halite dominated instead of rich in carbonates, and so that I would have that risk higher. So we can sort of talk about, from the n=2 sample size I've shown you here, and literally we don't know much about welding in academia. There's lots of industry data which is not published. So you can use those sorts of observations to try and place some estimates on whether it's welding or not. But I mean, I worked in the oil industry for 3 years, and it is just about handling a statistical risk, isn't it?
Thanks. So we have a question from Rachel Brackenridge. Why do some salt basins generate salt canopies? For example, Gulf of Mexico, whereas some do not, for example, the North Sea. Based on your salt weld facies, are tertiary welds generally non-permeable? Warn you, just a heads up, there's another follow-up from question from Rachel coming. We'll let you answer this one first.
Okay. So I think one reason you get salt canopies in some places and not others, simply put, is because it's related to the salt thickness. So you basically need to have enough salt to create the diapirs in the first place. So if you go to the Triassic salt, let's say offshore mid-Norway, the salt never was thick enough to really create diapirs, let alone canopies. You go to somewhere where the salt is very thick. I think the other thing that's important in addition to salt thickness is you need, one way you stop canopies forming is by sedimenting, right? So you're sedimenting in the mini basin, you're sedimenting around, you're sedimenting on top of the diapir, and that stops the salt breaking out and spreading to form a sheet or a canopy. So I think one thing that helps you is where you have depositional hiatus, okay? So you have pauses in sedimentation where the diapir and the salt within the diaper is still rising, but the sedimentation rate, the accumulation rate is low, and then that canopy can spread out. So I think that's really important. Another super important trigger for creating canopies, I think, is horizontal shortening. So when you squeeze a basin like this, the salt is weaker than the mini basins, so all of the strain is accommodated by squeezing the diapirs. So you push the salt out the top and it spreads. So I think that helps as well. So the Gulf of Mexico is a famous basin where you had shortening due to gravitational processes. If you think about the North Sea, the shortening in the North Sea was predominantly tertiary for the most part, and that was after the salt was already covered in this very, very thick, essentially Mesozoic succession. So you weren't able to breach the Triassic diapirs in those cases.
Thanks.
Yeah.
And here's the promised follow-up from Rachel. Also, is there a depositional control on where salt wells form? The Brazil example showed carbonates in the weld, but not in the diapier. Are local carbonate platforms controlling development?
Absolutely, yeah. So, yeah, we think. So I know Rachel's worked in the mid North Sea high area and like the salt pit basins of the southern North Sea. Yeah. So when you go from the heart of the salt basin where you've got predominantly halite, let's say, and you go to the fringes where you start to get more anhydrites and carbonates, in that kind of Goldilocks zone between the two, that's probably where you'll end up getting these very heterogeneous welds, would be my sort of prediction, because you probably have enough halite to flow and create diapirs and ultimately to weld, but you don't have enough like carbonates to kind of stop that process. So I think there's a very, very strong depositional control, because if you go into the carbonate platform margin, there's not going to be any flow at all. The halite's not going to be mobile because the bulk rheology of the Zechstein, in this case you're thinking of, Rachel, is going to be so, it's going to be so immobile, it's not going to go anywhere.
Thanks, Chris. The question from Abud Afifi, I ask you to look into the future. What is the future of the Gulf of Mexico? Will all the Luan salt become autochthonous?
Yeah, if only I had that crystal ball. No, I mean, no, I guess. I think there you've got a very thick sedimentary cover above the Luan. You've already in place the 6B, so the shallower level of Lochman's layer. You've probably got quite a lot of dissolution going on at the 6B escarpment, so the front of the tertiary, the front of the shallow salt is being dissolved. So I think you're still going to have salt tectonics being fed by the shallower level. I think that the autochthonous salt, the Luan, is all locked down beneath very dense sedimentary cover now. But we can come back in a few million years and have a discussion about who's right.
You can keep that webinar series going. So don't see any further questions upcoming through the chat window here. And this is my opportunity to thank you again for a really nice talk, Chris. I've certainly learned a lot about salts and why salt matter. And over to Maren for some final announcements.
Yeah, also from me, a final thank you, Chris. Now we're very pleased to announce the speaker of next week. He's Knut Andreas Lie from SINTEF in Norway also, who will talk about building an open source communique code. We call it MATLAB Reservoir Simulation Toolbox. So we are very much looking forward to welcoming you next week again. So have a nice afternoon.
Thank you very much, Erin. Thank you again, Chris, and we see you all next week then. Thank you.
Bye-bye.